Right, welcome back. So at the end of the last video, what we have introduced is a systematical way to turn the nonlinear data, which is a tree, into a linear sequence. And depending on the kind of rule that you can have a pre-order, you can have in-order, you can have post-order. You will generate different sequences. But I think one thing can be guaranteed is that once you have the sequence, each and every node will appear exactly one time. You will never miss any node. So one immediate use of this particular process, this traversal approaches, is that we can then systematically go through each and every node. And if our purpose is to search for certain information, we can use the traversal method for that. But of course, the issue is that if you actually do the searching by using the traversal method, it's not going to be very efficient. In fact, in the worst case, if you are unlucky, you may take the linear time ON to actually find the element that you're looking for or prove that the element is not inside the tree. The reason for that is very similar to the earlier comparison between the linear search and binary search, right? So if you use the traversal approach to do the searching within the tree, the most numbers of elimination that you can achieve for one comparison will be a single node. Every time you go through one node, you can eliminate that node only. But we recall that if we can apply a very similar design such that like the assumption that the list is sorted when we conduct the binary search, then every time we conduct one comparison, we potentially can eliminate half of the candidate from consideration. That will bring significant saving in terms of the complexity. We can go from ON to O log n, for example, right? So I think this is the major idea behind why we would like to have a binary search tree, right? So we want to, in a way, introduce certain sorted order on a nonlinear data structure such as a tree. So we can perform search within it and have a binary search tree like complexity, right? So this is the final tree type, the most specialized one, I would say, for this particular lesson. So we call it a binary search tree. So if you look at binary search tree, sometimes we call it BST, and a binary tree, they are exactly the same. But the only difference over here is that now we want to arrange the value inside the binary search tree in a special manner, right? So the definition or this special property we have will be defined again by using recursive principle. What we would like to ensure is that starting from the root level, we want to have, if the root level value at R is being specified, right? So we want this value at the root level to be larger than all the nodes at the that's within the left-hand side of this node. And if you look at the right-hand side of this root node, all the value must be greater than the root node, right? In other words, the root node R should be smaller than all the nodes in the right-hand side. And after that, right, this is the first level of the definition. After that, right, the same definition will be applied to the left subtree and the right subtree, right? Which basically means that this property, this binary search tree property, should be applicable at each and every levels of the subtree. So if we can achieve that, then we will call this kind of binary tree a binary search tree, right? So this is one example. Right, so we want to represent numerical order. So if you look at this particular tree, this is actually the tree that we have seen, very similar in last lecture. So we have a value at the root node, which is 29. If you look at this particular value, 29 is actually greater than all the value on the left-hand side. And then 29 is actually smaller than all the value in the right-hand side, right? So if you look at this subtree, this is subtree 1, this is subtree 2. All the value inside T1 should be smaller than the root value. All the value in T2 should be greater than the root value. And this property is defined recursively, which means that if you look at T1, the same principle will be applied to the root node again, right? This 14 in T1 will be greater than everything to the left-hand side and will be smaller than everything to the right-hand side. And again, you do this recursively. Then if whole tree satisfies this, then we say that this binary tree will be quantified as a binary search tree. It doesn't need to be value, right? In this example, we actually use alphabets. We store alphabetical information inside the binary search tree. And here we actually rely on alphabetical order to check whether or not this particular tree satisfies the binary search tree principle, right? So you can see that all the tree, although it all begin with A, they satisfy the binary search tree property that we have requested. So this is visually speaking how we define a binary search tree, right? So very straightforwardly defined. So in terms of the implementation is very similar to what we have before, just like a binary tree, but we just have this special functionality of searching. And then of course we have the special functionality of inserting and removal of the key. Because we want to, at the time we insert new information or we remove existing information, we want to make sure that the BST property is still maintained. All right, so we start with the searching. Right? Searching, this process is actually very similar to the binary search. Right? So what we do is that for a particular key that we are looking for, we start with the root node. If the key is actually greater than the root node, then we know that everything to the left-hand side will need to be eliminated, right? Because the key is already greater than the root node, and root node is actually greater than everything to the left. So we can then safely progress to the right-hand side. And to do that, all we need to do is to just call a recursive function. So we actually progresses from the root node to the right child of the root node, right? If the key value is actually smaller than the root value, then we know that the key value must be in the left subtree, right? So that would be the case over here, right? So in that case, again, we'll do the recursion, but this time we'll recurse to the left subtree, right? So if we run out of the node, then we will terminate, right? Because it basically demonstrates that you want to, for example, you want to go left, but there's no node at the left-hand side. It basically means that then the key must be missing from the binary search tree. So if we want to search, right, so this will be the recursive way of realizing the idea. So we have two base cases. The first base case is the case where the root value is the same as key, right? Immediately we return with the root. Otherwise, if the left value, the left child is not empty, and the root value is actually greater than the key, right? So this is the case that we talk about, right? Because key is actually smaller than the root value, so which basically means that the key must be in the left-hand side, right? And the first check is crucial, because unless you actually have a left tree, a valid left tree, you cannot do a recursion to the left-hand side, right? So if the left-hand side is not empty and the root value is greater than key, then we'll recurse to the left-hand side. And over here, very similarly, if the key is actually greater than the root, and then your right-hand side is not empty, then we'll do a recursion to the right-hand side. If none of these are possible, it basically means that, for example, you try to go left, but left is empty, or you try to go right, but right is empty. Then this is the indication that the information you try to search for is actually not inside the tree. So complexity over here, again over here, if you follow what we have learned earlier from the binary tree, it might be tempting to say that the complexity will be log n, right? So this is based on our earlier example, because roughly speaking, what you have is the elimination of half of the element every time. So if you repeatedly just reduce the size by a factor of 2 every time, then the complexity that you have will be log n. But again, over here, later you'll see that this might not be always the case, right? Depending on how the tree is formulated. For certain special shaped tree, your complexity may not be so good, right? So we'll defer this to the later slide. But now just assume that, okay, because it actually eliminates, roughly speaking, half of the node, so the complexity should be close to big O log n. Okay, so this is searching, right? How about insertion, right? So if you want to insert a node into a binary search tree, basically what we will need to do is that you first will try to do a searching, right? So again, over here, one of the assumptions is that the information we want to insert into the binary search tree, it should be different from all the existing information, because if you have a duplicated information, binary search tree will not be able to place it, because there's no rule as to like where should you hold the information, the value that's of same value to the existing value, right? There's no place for that. You either have to be smaller or greater. You cannot have a tie, right? So assume that the new information you try to insert is different, right? Then what we need to do is that you just perform a regular search within binary search tree. The moment you reach a none, I mean, for example, you should go left, but the left is actually empty, then that is the indication that this is the place that you should put down the new value, right? So let's try one example. For example, let's say we would like to insert the new information of 1, right? So you can search starting from 2029, then starting, I mean, 1 is smaller, so you go left, 1 is smaller, so you go here. Then you can see that, I mean, because 1 is smaller than 2, so I should go left, but left currently is empty, right? So this will be the place that I put down my new node 1. All right, so I just cross it out. This is the place that I'm going to create a new node and store the new value in, right? Should be the place, right? So another example can be, for example, let's say you like to store the new information of, let's say 35, right? Again, you follow very similar process. 35 is over here. You start on the root node. 35 is greater, so you go to right-hand side. 35 is smaller, so it should go left-hand side, but left-hand side right now is empty, right? So now this basically indicates that this is the right place to put down 35. All right, so this is, I think, very straightforward. Essentially, it's almost identical to the searching process, but you don't terminate when you encounter a none as a result. What you do instead is that if you encounter a none, then that's basically the place that you should create a node and make an attachment, right? So in this particular code over here, this is what we will do. What we were previously doing is that before we do the recursion, right, we are going to check whether or not the left-hand side is empty, right? This is the case where if a key value is actually smaller than the root value. So we further divide this into two cases. This is case 1, this is the case 2, right? So if the key value is smaller than the root, and, right, in the secondary case over here, right, secondary check over here, and the left is not empty, then we will make a recursive call. But on the other hand, if I should go left, but the left currently is empty, then it means that this is the position I should actually insert my node, right? So I create a node with the key value. Then for the root value I'm currently comparing to, I will set the left-hand side, which is currently empty, right, as the new node. And I will return this newly created node as the return value. For the right-hand side, we do exactly the same, right? So if the right-hand side is not empty, then we do the recursion. But if it's otherwise, the right-hand side is empty, then we will create a node with the key value, and we set the right-hand side of the root to be the node itself. Okay, very similar. Right, so insertion is almost identical to the search, but removal of the node will be more complicated because there are multiple cases we need to consider. So the major thing that we have to consider is that after the deletion of the node, we have to make sure that when we reconnect, if we make any, like we generate any gap, right? Because you delete any node, you're leaving an empty space. You have to fill that node, that empty space with certain node. When we fill that empty space, you have to make sure that the original binary search property are still being maintained. Okay, so the first thing that you do is that, of course, when you are about to remove a node, first thing is to identify where is that node, right? So this is the second step. You have to traverse to find a node. Now, once you have identified that node, then what you do is that you have to check for one of the three different cases. Case number one, if the node is the leaf node, for example, 2 over here, right, is the leaf node, or the node has a single child, for example, 24, right? If you want to delete 24, 24 is one example that you have a single child. Finally, the third possibility is that the node you try to remove has 2 children. 14 is one such example, or 29 is also one such example, right? So they need to be handled differently, and we will discuss them one by one. So if the n value is actually a leaf node, this is a straightforward case, right? All we need to do is to directly set the parent's corresponding pointer to be none. Then we achieve the purpose of deletion, right? So next page over here is the case one, right? So in this particular tree over here, let's say we like to delete 40, 20, or 100. The deletion will be straightforward. You simply say instruct node 30 that you just set your right hand side, instead of 40, you set the right hand side to be none. Okay, so this is case A over here. For case B, right, so this is the case where you have only one child, right? So if you're only one child, this is the solution we have to maintain the order. We will just say that for that particular node n that you try to delete, you identify the parent, you identify the child, and you will connect your parent to your child, right? Your parent, in other words, will take over your child. So we can look at the example. Again, the same trees example. Inside this particular tree, let's say we intend to delete 90, right? So what we will do instead is that we will identify the parent node, right, which is 50. We identify the child node, which is 100. Then we do the reconnection. We set the right-hand side of 50 to be my right-hand side of the child, right? Or this single child can be to the left-hand side, doesn't matter, right? Potentially, for example, you can have 80, right? And then you suppose you don't have 100, you have 80. Then what you do is also the same, right? You take your child, reconnect it to your parent, right? The reason why you can do that is that if you are right-hand side, you're deleting a single child node on the right-hand side. Remember, like based on the BSD property, right? Everything to the right of the root node will be greater, right? So although this node over here can be left-hand side, can be right-hand side, but the value will still be greater than the root node, right? So the connection will not be an issue, right? So here you connect 100, here you connect 80. You will not violate the BSD property. All right, so this is the case where you're deleting a node, but with a single child, right? Okay, so finally, we look at the third case. For the third case, this is the most complicated case. You have 2 children. So you have to choose who to take over n's location. Here, we actually have 2 potential candidates. You can either choose the leftmost node of the right subtree or the rightmost node of the left subtree, right? So why that's the case? Okay, so think about that for a minute, right? So let's try to visualize this. Let's say this is the n that you try to delete, and right now this n is connected to the left subtree and the right subtree. You want to delete the node n, right? And node n actually have another parent over here. Let's say the parent's here. Okay, so if you want to find a node to take over n, right? And you want to find that node in the right. This is the right subtree. This is the left subtree. You want to find this node in the right subtree. You want to make sure that that particular node, once inserted, taken over n's place, you will still satisfy the BST property, which basically say that everything on the right hand side should be greater than the new node, right? And everything to the left hand side should still be less than the root node. And to ensure that, what you need to do is to find the smallest element in the right hand side tree, right? Which is the leftmost node. The leftmost node in the right hand side tree will be the smallest element in the right subtree. If you use this to replace n, then guaranteed that this new value will still be greater than everything to the left, but smaller than everything to the right. Okay, and this is also the reason why, if you plan to pick the node from the right hand side, from the left hand side to replace n's place, you should choose the rightmost value. Because this rightmost value over here will be greater than everything in the left hand side. It's actually the largest value in the left tree, right? But at the same time, because it's actually at the left hand side of n, so guaranteed it will also be smaller than everything to the right hand side. So both value will be valid, right? So it's up to you as to like which one will be better. Later we'll say, we'll give you a hint as to like if you have these two like equally okay choices, which one should you choose? Okay, so let's probably look at this particular example. This is the case 3, right? So for the first case, right? So let's say now we would like to delete the value 30, right? So what you do is that, let's say you like to pick the node from the right hand side subtree, and this right hand side subtree, right? So again, following the principle, you want to find the successor, right? This successor will be in this case the largest value, the smallest value in the right subtree, right? So it will be leftmost node in the right subtree. In this case, 40 is the leftmost node, right? And it is actually indeed the smallest value in the right subtree. You can ask 40 to take over 30, right? If you ask 40 to take over 30, then basically you leave another place, right? And if you look at the empty spot left by 40, for the case of 40, right, effectively it's as if you're deleting 40, so 45 in this case will take over 40's place, right? So 40 take over 30's place, and 45 take over 40's place. Okay, so this is like essentially, we delete 30, but effectively along the process, when we are moving 40, we actually just almost like artificially did another deletion, and then we use 45 to fill the space, right? So we delete one node with 2 children, and then along the process, because we move 40, it's as if we are deleting the node 40, which comes with a single child, 45. Right, so this is the first case. The second case, right, so it's also possible that the node that you try to use actually is actually from the deeper content, right? So it's not immediately to your right. So what you'll do is that, okay, so if you look at this right tree, right, so the right tree, the smallest, the leftmost element in the right tree is actually 35. And this 35 is not your immediate right, right? So what you need to do is that you assume that 35 will be deleted, right? And then 35 will be used to fill the vacancy that's caused by the removal of 30, right? So once 35 is up, then effectively you are like running through the process of deleting 35, right? By deleting 35, you see that is effectively the same as deleting a node that's with a single child, right? So, and this single child will just simply take over the previous previous value's place, which is 35. So 37 will actually be linked up to the 40. Okay, so that will be the rule, right? So slightly more complicated, but if you are careful enough, you can actually come up with all the details. Right, so in the interest of the space, we didn't provide like complete code listing. But if you want to read more about this process, you're welcome to follow this book over here. It talks like comprehensively about like how what will happen when you delete an element from the binary search tree, right? Okay, so finally, we go back to this topic that we touched on earlier, right? So we didn't really definitely put down the complexity of binary search, although we roughly say that, okay, similar to binary search. So searching in the binary search tree should also have login. But at that point, we put down a question mark, because the real complexity of the searching operation in the binary search tree, and for that purpose, also the insertion or deletion, right? Because insertion, deletion also require you to execute a search first, right? Actually depends on the shape of your tree. So if you look at the left-hand side, right, this is relatively balanced tree, right? So you actually have, roughly speaking, same numbers of levels in the left-hand side and right-hand side. They are more or less like stuffed, right? It's very close to a perfect binary tree. You have very little vacancy. In this case, your height will be closer to like the log of n, right? So the searching of the complexity as a result will be closer to log n, because again, one of the property of the binary search tree is that for each generated level, you will visit at most one node, right? For example, starting from the root node, for the next level, you have to choose one node. And once you pick one node, again, in the next level, you pick at most one node, right? So although you can have a lot of nodes in every level, but every level you'll pick at most one node, actually exactly one node, right? So because of that, numbers of levels determine the complexity of your search operation. So the higher the height, the higher the complexity. Your complexity really depends on not the numbers of nodes per se, but the height. Right, so if your height is log n, then you'll have log n complexity. But in this case, right, if you look at your height is actually closer to n, right, because it's almost like a ridge, right? So you only have almost exclusively right-hand side filled with element, left-hand side are almost all empty. So your height is actually n-1 in this case, right? So if you look at your complexity, it's going to be OH, but in this case, because of the shape, it's going to be closer to ON. Right, so this is a very important takeaway. So when it comes to binary search tree, the height, the shape of your tree will determine the complexity. And this is the reason why I think if you read more into the deletion or the insertion of the element inside a binary search tree, one important, I think, improvement for the more advanced version of the binary search tree operation is that we will use that as a chance to adjust the height of the tree. And the purpose of the adjustment is to make the tree more like what we have in the left-hand side. So we'll do a rotation whenever possible to adjust the tree height so it can actually contain as many nodes for a given height as possible. Whenever possible, we will try to eliminate the height. Okay, so this is the binary search tree. Right, so we have some practice for you. Again, more in-class exercises. We'll pause here, right? So I will encourage you to actually go over the experiments that about like different sequences in which you're going to insert the element. The data type, the data element, if you look at it, they are exactly the same. But due to the sequence, you're going to generate different kind of binary search tree shape. And as we discussed in the previous slide, due to the differences in the shape, the actual searching operation might lead to very different kind of performance differences, right? So 1 and 2 basically help you visualize that. Okay, number 3 is the algorithm design question, right? Very well-known one. So try to think about how do you use the assumption about that's behind the binary search tree to check a given binary tree as an input and return true and false, indicating whether or not this binary tree is a binary search tree. Again, important property that you are checking is to make sure that the root value should always be greater than everything to the left-hand side and should be smaller than everything to the right-hand side. And this property need to be recursively true. Okay, so think about this. then try to, I think the easiest way to materialize and to utilize this particular observation, this property, is by recursion. Think about how you can use recursion to achieve that. And we'll review the other solutions separately. Right, finally, just to summarize what we have covered for today, we have introduced the very first data type. Now you are able to handle the relationship, and that relationship is not linear, right? More specifically for this week, we are dealing with hierarchies. Next sessions, as you will see, we're going to handle arbitrary linkages between different individuals. This is what we call a graph. So very important operations for the nonlinear data structure is that how do you come up with the sequence that guaranteed you're going to go over each and every node exactly one time, right? So this kind of operation is called traversal. You can systematically perform the traversal according to the designated logic. You can do it in pre-order, in order, post-order design. Right, so make sure that you understand how to execute them and what is the difference between them. Finally, we introduce the binary search tree. Right? By imposing the binary search tree property, we can actually enable you to search throughout the tree more effectively. All right, so next week, actually next session after the break, we are going to enter a more complicated data structure. Then we will have a complete overview about like everything that will be made possible by having this data structure with increasing complexity.